see everybody here today. For those who don't know me, my name is Swapna. I am the meeting coordinator for all the meetings that happen at the center. And my partner in crime, Rob's here too, to make sure that all the technical pieces are working. I just want to welcome everybody here. This is our first speaker of the 24-25 speaker series. So welcome, Alex. So today we're going to hear about climate conditions on Mars. Alex is a PhD candidate at York University. Alex is a planetary scientist completing their PhD at York University studying the Martian atmosphere. They are a collaborator on the Curiosity rover and take part in science operation planning, as well as being the lead on the environmental science team. Alex has also been helping to develop an instrument which will study the origins of mysterious Martian methane. In addition to their studies, Alex is a member of the organizing committee for ComSci-ConCan, a science communication workshop for Canadian graduate students. With that, I welcome Alex.
Thank you very much. I'm excited to be here to talk to you guys about methane.
Is that too dark?
No, this is fine. So yeah, as mentioned, part of my PhD research is looking at methane on Mars, which is a bit of an enigma. So I'm going to give you an overview of that enigma and then talk a little bit about how I've been studying methane on Earth to try to help understand what's up with methane on Mars. So when you think about methane on Earth, you might think about things like farm animals. You might think about things like fossil fuels. This just kind of illustrates some of the sources of methane that we see on Earth. And another thing that you might think about with methane is climate change. So methane is the second largest contributor to like greenhouse warming. And methane has been rising on Earth over the years. I actually heard a story on CBC a couple of weeks ago, and I thought, oh, I'm giving a talk about that. That's keep that in mind. But yeah, so there are a number of initiatives tracking methane on Earth for specifically climate change reasons and looking at different emitters and how we can manage that. But we're not talking about Earth. We're talking about Mars. Mars is a very different place to Earth. This shows the very thin Martian atmosphere at the limb here. I think it's very beautiful. But it's a fairly different situation than what we have with the atmosphere here on Earth. So it's much, much thinner. And we have much colder temperatures. We have much lower pressure. This is a weather report from Curiosity from a few falls or days ago. We also, we do see things like we see on Earth, like clouds. So here are some clouds, but these are actually carbon dioxide clouds, not water. We do see water ice clouds, but we do, yeah, as I said, get a lot of different conditions in the Martian atmosphere than we do on Earth. Another important thing in the Martian atmosphere is dust. So very fine dust gets lofted into the atmosphere and just kind of hangs out there, and it drives a lot of processes on Mars. So we get things like dust devils, and we get things like global dust storms, where the entire planet becomes just encircled by a great amount of dust. But also the dust on Mars leads to more subtle things. So it affects the amount of radiation that's getting down to the surface. It creates different seasons. So we kind of have two seasons on Mars, a cloudy season and a dusty season. And it can also impact the amount of different molecular species in the atmosphere. So the atmospheric makeup of Mars, again, unlike Earth, majority carbon dioxide. We've got a little bit of nitrogen, we've got a little bit of argon, and then we've got a little bit of other. So these other trace gases are things like oxygen, which is actually the fourth largest species on Mars, things like water vapor, and things like what I'm talking about here today, methane. So we haven't actually known about methane on Mars for a very long time yet. It's only been a couple of decades that we've been actually observing it on Mars. So this is one of the earlier observations. There's some controversy with methane. So some claim to have seen it in the 90s. Some claim like this one is from 2003. And various people believe or don't believe or believe some of the observations. It's all a bit murky. For the purposes of this, I'll be touching on a few historical observations, but also I won't be getting super into the controversy with methane. If you want, you could talk to me about that later. It's not particularly relevant at this juncture. But anyway, in 2003, the IRTF, which is the telescope on Hawaii, observed a methane in the Martian atmosphere. 19,000 metric tons of it. To me, I'm not entirely sure what that means. It's closer to, the better way to think of it is in parts per billion. So the largest plume they observed was 45 parts per billion. This is the same image that I had on my cover slide. So this red area here is the plume. You can see it's kind of near the equator. And they observed this spike of methane here, and then it kind of dissipating around the rest of the planet in the northern summer. So that was very interesting. It caused quite a stir in 2003. And then again, so this paper wasn't actually published until 2009, and it caused kind of another stir. But between the actual detection and that paper being published, we had another detection from Mars this time. So this is with the Mars Express orbiter with an instrument on it called the Planetary Fourier Spectrometer. Mars Express is a European orbiter. It has been at Mars for many years. So in 2004, it saw an amount of methane on order 10 parts per billion. This was actually the first published methane detection at Mars. So recall that the 2003 spike wasn't actually published until 2009. And when this got published and when the Earth-based observation got published, that's when observations started kind of coming out of the woodwork, like, oh, maybe we saw something in the 90s, maybe we saw something some other time. This observation was also made at a completely different location on Mars. So at that point, people are kind of thinking, okay, we've had a few observations. What is up? Where's this methane coming from? What's going on here? Then Curiosity got to Mars and also saw methane from the surface. It saw much less. Gale crater where Curiosity is also near the equator, but it was not the same location that the 2003 spike was seen. So we've got a number of observations that aren't super agreeing in time, in space, in amount. So it's unclear what is going on with the methane. There are a number of possible methane sources. Obviously, the one that maybe people's minds jump to first is biological. So maybe there are little microbes under the surface of Mars producing methane. But there are also a lot of non-biological methane sources. Things like reactions in the subsurface or even on the surface itself. Also, in the past, Mars was much warmer. It had a much thicker atmosphere. It could have potentially supported life. We haven't found evidence that there was life, but it was habitable. So if methane had been sequestered within the subsurface in the past, it could be now kind of coming out. The problem with methane is that it breaks down very easily in the atmosphere. So it has reactions with ultraviolet light, it reacts with oxygen, it turns into different things. So methane in the atmosphere only lasts, in the Martian atmosphere only lasts at most 300 years. So if there was methane in the very distant past, geological time, billions of years ago, it should not be there. So this means since we're seeing methane now, it is being produced somehow. It's coming out of the subsurface, it's being produced through some kind of reaction currently, which is very cool. But we don't know how. This is where curiosity has been a big help. So that diagram I just showed you had a lot of stuff going on in the subsurface and near the surface. Curiosity is on the surface of Mars, and it has an instrument that can detect methane. It is the only instrument currently or ever on Mars that can detect methane. So it can be detected from orbit, it can be detected from Earth, but this is the only thing that can be right down on the ground where the methane is. And where that is in Gale Crater, which, as I said, is just south of the equator. I like Gale Crater because you can see it from orbit. It's this thing right here. It looks a little bit like a crescent moon, and it's got the dust tail coming down from it. So it's very easy to find if you have an image of Mars. Gale Crater is a little weird, which I will talk about a bit more later, but the atmospheric interactions around it are just a little strange. It's a very large crater. It has this 5-kilometer mountain in the middle. And that just causes some of the atmospheric mixing in it to not behave as it does elsewhere on Mars, which is kind of interesting. So we have our rover studying methane, and what it's using to study this is an instrument actually inside the body of the rover itself, called the Sample Analysis at Mars Suite, or SAM, very friendly name. This is about microwave oven-sized suite of instruments. It is extremely complicated looking. Anytime you see like a technical diagram of it, it's just incomprehensible. I applaud the engineers who at Goddard who worked on it because they are geniuses. But specifically what we're using to look at the methane is, so there are a number of instruments on SAM, and we're specifically using the tunable laser spectrometer. And the way that this works is that it has a laser within it that bounces back and forth between mirrors a number of times, I think about 80-something times, to create a longer effective path length, and that gives it more room to examine the molecules within the chamber and analyze them and figure out what's in there. So it's used for a number of investigations. SAM primarily is a geological instrument. So when we drill on Mars, we get samples and they're actually delivered directly to SAM, which then analyzes their composition. But we can also use the tunable laser spectrometer to ingest atmospheric samples and then analyze them, which is really cool. Unfortunately, this is a slightly difficult process. The ingest, so the process that it goes through is it ingests atmosphere, and then it enriches the atmosphere, and then it measures it. And this takes several hours, and we really only get one sample out of that. Also, it is fairly power intensive. So whenever we run these experiments, it takes up a lot of our day. So I work as a planner on the rover, a science planner. And when we have a SAM experiment coming in, we know about it in advance because we're trying to build up enough power so that we can do one of these. And also because it's so power intensive, we like to do it overnight. So we're not worrying about getting in the way of other things. The overnight thing will become relevant in a little bit, so hold on to that. Anyway, despite these challenges, we've been able to get a number of methane observations. This is a fairly old figure. After only 3 years on Mars, 3 Mars years on Mars, sorry, we've now been on Mars for over 5 Mars years, or over 12 Earth years. And we've got 20 methane observations, maybe more. But what we're able to see from these is this seasonal methane cycle, which is really interesting. When you see this kind of seasonal cycle, you assume that there's something going on to create the methane and to destroy the methane in such a way that you get a cycle like this. It's not just methane hanging out. There's some kind of active process going on, which is really interesting. And it's only with these kind of regular measurements from SAM that we're able to build up the image of this cycle, which is really cool. The other thing that Curiosity was able to do is when it arrived, the Mars Express was still doing its thing in the atmosphere, and we were actually able to see a plume of methane with Curiosity that the planetary Fourier spectrometer from orbit also saw, which is the only time that 2 instruments have agreed about seeing methane. The European Space Agency put together a nicer graphic about this, so I just stole that. But you can see that it was only a day later that Mars Express also saw this methane plume, which is really cool. So this is maybe something we would want to repeat, having confirmation of methane from the surface and from orbit. And a way that we attempted to do this is that the European Space Agency, again, sent an orbiter called the Trace Gas Orbiter. And as the name suggests, it was to look at trace gases, not just methane, but things like oxygen, things like water vapor. When TGO arrived a few years ago, it started taking measurements, and a big part of its mission was to look for methane. So we have Curiosity in Gale Crater, seeing methane, all good so far. And then we have TGO in orbit, not seeing methane. So TGO has a fairly good detection limit. It can see all the way down to about 5 kilometers above the surface, and it can theoretically detect methane as in amounts as small as 0.05 parts per billion. So remember that we're seeing around, we're seeing more methane than that in Gale Crater. So it's a little strange that TGO is not seeing methane, and various people put forward suggestions for why this is the case. Maybe Curiosity is wrong and not actually seeing methane. This is unlikely. The SAM team and the Curiosity team have done a lot of due diligence looking into potential sources of error or things with the instrument that could be causing a false detection, and it's not likely the case. It could be that TGO there's something wrong with it, that it's not seeing the methane. This also seems unlikely. The TGO team has also done a lot of due diligence looking into, okay, is there something up with our instrument? What's going on here? So if TGO is right and not seeing methane, and Curiosity is also right and seeing methane, that seemingly does not make sense, except maybe it does. And the answer to this could lie in when these measurements are being taken. So Curiosity, as I said, the SAM process is very power intensive. We do it overnight. We do it fairly infrequently. TGO is taking its measurements during the daytime, usually around sunrise or sunset. And actually, when we took daytime methane measurements with Curiosity, we saw an almost non-detection of methane. So very, 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 very low levels compared to what we're seeing at nighttime at a similar time of year. So that's where we get to this diagram, which I'm going to step through. So in the atmosphere, you have what's called the planetary boundary layer. And that's the area of the atmosphere that's closest to the planet, that's impacted by things like topography, that's impacted by what's going on in the surface. And it is, there's quite a lot of mixing that goes on in the planetary boundary layer. We have one on Earth, we also have one on Mars. During the daytime on Mars, the planetary boundary layer is fairly high. It's actually about the same height as the planetary boundary layer on Earth, which is interesting. At nighttime in Gale Crater, the planetary boundary layer collapses, basically. It goes to much, much closer to the surface. So this is also the time when we're seeing the methane rising, the amount of methane rising. So what's probably happening here is during the daytime, the methane is being mixed around in the planetary boundary layer and it's spreading out all throughout the atmosphere, all throughout the planetary boundary layer. So at Curiosity and potentially where TGO is looking, the methane is just too spread out to be able to see it. Whereas at nighttime, when Curiosity is looking at the methane, there's not as much mixing going on, and it's sticking really close to the rover. So that's why we're seeing more methane at nighttime and less in the daytime. And that's potentially also why TGO is not observing the same things that we are. And the models of this actually line up really well with the observed methane at Gale Crater, which is neat. So we've seen some methane, we have a seasonal cycle, we have a diurnal cycle, a daytime-nighttime cycle. What are we missing? Well, we still don't know where the methane is coming from, and we also don't really know where it's going. It is being maybe mixed a bit away by the atmosphere, but it seems like there's some destruction mechanism going on. So returning to these plumes, Curiosity has also observed plumes of methane. So it observed a plume one day, and then a few days later, it took another measurement, and there was nothing there. So these plumes are arriving and leaving very, very quickly, and we have not been able to see the start of the plume, and we've not been able to see the end of the plume. We've only caught them in the middle. And the only reason we know they're there is because we're suddenly seeing a bunch more methane. So this is a mystery. There's mysteries about where the methane is coming from, where it's going, as I said. This is a diagram I shamelessly stole from my advisor, kind of showing what some of the areas that we have information on and some of the areas that we're missing. So these plumes live in this high frequency time zone. So methane also, the mysteries about it are on timescales less than a day and near the surface. And we'd like to understand that a bit more. And one way that we're attempting to learn more about that is with different instrumentation. There's currently no active plans for anything like SAM-TLS or better than SAM-TLS to go to Mars. So we have been developing this instrument called MAGE. We love an acronym. This is the Mars Atmospheric Gas Evolution Experiment. And MAGE is another kind of spectrometer that's developed by ABB, which is an engineering company that makes a bunch of things. They make like transformers and things, but they also make these spectrometers. So I mentioned with SAM-TLS that it bounces a laser back and forth about 80 odd times. This spectrometer bounces it back and forth many, many more, has a much larger path life. It's able to, it has a finer resolution for detecting methane, and it does not take 5 hours to take one measurement. It can take more continuous measurements. So that's great. So if something like this was to go to Mars, we might be able to probe that higher frequency, smaller time period area that we're missing. And we might also be able to see things like a plume initiating and decaying. So to test this instrument, a couple of summers ago, we sent it up to the Arctic. And at this point, we're taking a small break because I just gave you a lot of information about Mars and we're playing a game that I invented, and this is called Minute or Mars. So here we have a picture near Resolute, and we have a picture in Gale Crater. So I'm going to show you some pictures, and we're going to guess if they're Nunavut or Mars. Just call out your answers. So, number one.
Mars.
Correct. Number two.
You're the Nunavut.
Yeah, you guys are so good at this. Okay. It's
Mars. Yes, Mars.
This one is actually Nunavut. And then finally, yeah. When I got up to Resolute 2 summers ago, I looked at the landscape and I thought, this reminds me of things I've seen in Gale Crater. And so I took a lot of pictures and put together this kind of silly game. Okay, back to the science. So to study methane on Mars, we actually ended up sending this instrument to Mars, the McGill Arctic Research Station. You might notice it doesn't look a ton like Mars. Where this research station is located is on an island in the high Canadian Arctic called Buming-Magnunat, or Axel-Heiberg Island. It is very far north, about 80 degrees north. It takes a while to get there. Canada's big. So the way that we did this, this is the travel log portion of the talk. So we started in Toronto. We took a train to Ottawa. Here is the research team I went up with some of our stuff, not all of our stuff, in Union Station. From Ottawa, we flew to Iqaluit. I was with 2 geologists, so we spent some time looking at rocks. From Iqaluit, we then took the milk run to Pond Inlet, to Arctic Bay, and then finally to Resolute. We then got stuck in Resolute for about a week longer than we expected. But that was fine because we got to go on lots of hikes. I took some photos, as I said. We got to go out on the sea ice. We actually got to celebrate Nunavut Day, which was with the community, which was very cool. Saw lots of animals. The reason that we got stuck there was because the weather was very bad that year. It was extremely wet, and we could not actually land a plane on Axel-Heiberg Island. But finally, we did make it up there with our trusty twin otter. So the reason that we were trying so hard and for so many days to get to this specific location is because of these 2 sites, and these were our study sites. So we have the Gypsum Hill Springs and Wolf Spring, and these are hyper-saline, very salty, cold springs. What's interesting about these springs, so they're very salty water, as I say, coming up through the permafrost, and they actually maintain a very kind of even temperature throughout the entire year, even as temperatures are fluctuating quite a bit through the Arctic night and then in the Arctic day in the summer. It's just, yeah, so these springs maintain a temperature a little bit above freezing. And the other thing that they have is methane bubbling up through them from the subsurface. And this methane is probably produced by a combination of microorganisms and geological processes. So we wanted to study these. These have been used in a number of studies as a Martian analog, and we specifically were interested in studying the methane in them. So this is Wolf Spring. As I said, it's a Martian analog. Again, this doesn't look a ton like Mars. We see liquid water, we see green stuff. So why are these used as Martian analogs? One reason, sorry, this is probably what you're expecting to see with Mars. It's very dry. There's not a lot going on. But it might not actually be as dead and dry as all of that. So these are also images from Mars of these formations that look a lot like they're made by rivers or something. So this paper that has these images in it talks about these landforms. I'm not a geologist, so bear with me for a second, but these landforms seem to have been formed by more recent fluvial processes as opposed to something in the distant Martian past. So Malin and Edgett talk about recent groundwater seepage at Mars. So this is a potential explanation for these features. This other scientist, Nick Hoffman, had another idea about these features, that they could be formed by subsurface brines. So very salty water under the surface of Mars. You might recall the springs we're looking at, very salty water from the subsurface. So in this way, the springs and the permafrost and that cycle is a very good analog for Mars geologically. Which is of note, but I'm also mostly interested in the methane. So you can see this is the Wolf Spring, and you can see bubbles coming up occasionally. And this is the gases being released, methane and other gases being released in the spring periodically. So at both locations, took my little instrument, which, as you can see, did not work entirely well. I have this external battery for it because the battery that it came with was broken. There were a number of challenges. It's kind of like being on Mars. We have a number of challenges there too. But I was able to take a number of measurements at both locations to kind of see how the methane was interacting in and around these springs. So what we saw, the blue are the actual methane measurements that we saw. The orange line is a kind of average that I made. So you see these huge spikes of methane, and those correspond to when those bubbles are bursting at the surface and releasing more methane into the atmosphere. I was honestly not expecting to see that. It makes sense afterwards when I kind of thought about it, but I was expecting more of a steady amount of methane. So already I'm seeing with this instrument that I can see things that we just don't see on Mars. So these instantaneous spikes of methane and really small time scale changes in the amounts of methane too, which was really cool. The other thing that I did was at both locations, I took a number of measurements at different locations around the spring. So in this one, we have our wind going across the spring. I took a measurement upwind, I took a measurement downwind, and I took a measurement inside the spring. Beside the spring, not inside the spring. So upwind, we see basically no methane. Whenever we explain this, I think that it sounds obvious, but it was cool to see because it confirms that we can actually very strongly see the methane signal. And when we're upwind of it and there's no methane being brought to us from the spring, we're not seeing anything. But when we're downwind and the methane is being brought by the wind, then we can see it. So if we didn't know this spring was here, we might be able to infer that there was a methane source somewhere in between those two measurements, which is interesting for Mars because we don't know where the methane is coming from. And then again, we're seeing these spikes of methane. So we're seeing the methane being produced in real time. And the other thing that's interesting is that upwind and at kind of more background locations, the up and down spikiness, the variability is not there. But at the spring and downwind of it, we are seeing that variability. So we can see not only that there's methane being produced there, but we can also tell something about how frequently it's being produced. This is the same information, but in number form. So again, upwind of the spring, low amounts of methane, low variation. At the spring, extremely high amounts of methane, extremely high variability. And then downwind, a bit more methane, a bit more variability, but nowhere near as much as the spring. So what does this mean for Mars? As I said, we're able to see the signature of a methane source in space. So if we know something about how the wind is moving, about how much wind there is, about how the atmosphere, the air masses are moving around, then potentially with observations like these, we could actually localize a source of methane and either go there and see what's going on, or just know that that's where the methane is coming from and figure out what's going on there. Also, clearly with methane, the small timescales are important. We're seeing a lot of movement on like very, very small, on order a few seconds timescale. And that's something that we're just not capturing on Mars right now. So it is important that we see these smaller temporal changes in the methane to understand where it's coming from and what's happening there. So with something like this, we might be able to get much more information about where the methane is coming from, how it's behaving, potentially how it's being destroyed. And maybe that leads to the discovery of life. Maybe it's geological, but it is filling in like another piece of the puzzle about the Martian atmosphere. So that brings me to the end of the talk. A lot of people contributed to this work. Some of them are graphically displayed up here. There's many more. But yeah, I'm very grateful for everyone's help. I'm grateful for your attention today, and I think we're gonna have a break and then I'm going to take questions.
Yeah. So we'll start a Q&A. So who'd like to go first? Okay, Rob can go first.
So my question is, with the carbon or the methane, is it like a cycle or is it just a one-way trip and then it's just, you know what I mean? Like, yeah, that's my question.
So on Mars,
Yeah, on Mars.
so it looks like it is cycling. I guess.
What's coming out of the atmosphere and then back into.
Oh, yeah, okay, potentially, unclear. So yeah, it could be that it's being produced or like continuously coming out of the subsurface at different rates at different times of year. It could potentially be being like sequestered back in, or it could be just be being destroyed. I definitely don't. I'm assuming the community in general also does not know the answer.
Thanks.
Yeah.
I could bellow from there, but the springs on Axel Heinberg Island, those deposits those were salt deposits, right?
Gypsum.
Gypsum, interesting. So the salinity of those are very high. And those were cold springs, right?
Yeah.
Okay, interesting.
Yeah. I wish I could speak more to the geology, but I really cannot.
Okay.
Great job, Alex. Okay, I'm going to throw you off. I'm not going to ask you the question I said I was going to ask you. What drove you to want to get into studying methane and atmosphere, Mars atmosphere?
So I had a very, I don't know, maybe it wasn't a weird path. I studied engineering in my undergrad. And then I thought I'm not very into engineering. I kind of want to go more into the sciences. I do feel like I almost stumbled a bit onto atmospheres in general. I was generally interested in space. But I did undergraduate work with actually my current advisor, looking at wind features, so features shaped by wind on the North Pole of Mars. And that was very cool. And, I was actually really, I still do love the Martian pool, and kind of the more geology side. But the work that I do with the rover, and the work that my advisor does tends to be more atmospheric. So yeah, it does kind of feel like it was a bit random, but because I didn't study atmospheric science or anything like that. But I don't know, it's really, I really enjoy it now. And I make a lot of jokes about not being a geologist and not understanding what geologists do, but I do feel like I could have very easily gone that way. It was just, sometimes things are a bit random.
Archie? Okay, so where do we go from here as far as explaining the methane on Mars? And that's part 2A. And part 2B, where do you go next with your career?
Part 2B is a scary question. To answer your first question, it's so obviously we like to get actual measurements. We like to have instruments there actually studying things, but it takes a very long time to get a space mission together. Curiosity, for instance, was conceived of in the very early 2000s, and didn't get to Mars until 2012. So it takes a while to get anything there. Obviously, we can keep taking measurements with the instruments that we have now and keep building up our understanding that way, but if we want anything new, it's gonna take a while. So what's kind of happening in the meantime is a lot of modeling and a lot of experimental work on Earth, so simulating conditions on Mars and seeing how different inputs and stuff respond, and kind of testing theories that way. So through either computer models or through laboratory simulations. So I think it's going to be a lot of that until we get more data from Mars, which could be a bit slow going. We'll see. A few years ago, methane was a really kind of hot issue that a bunch of people were interested in and talking about. These days, the big thing on Mars is Mars sample return, which might happen at some point. It will happen at some point. So different things take on different amounts of importance, which makes it tricky sometimes when you have a specific thing that you're really interested in, because maybe the community is actually interested in something else right now. But there's always something you can do, like examining old data or as I said, like doing models or things like that. In terms of my career path, I have a little over a year left in my PhD, and my advisor keeps asking me what I'm wanting to do next, which I really love the work that I've done with mission operations and things like that. So if there's a pathway forward for that, what is interesting in Canada specifically is that we're doing a lot of lunar stuff right now, and Canada is actually sending its own lunar rover to the moon. So there are opportunities coming up there to be involved more on the mission side of things. And obviously there are opportunities like in the States and in Europe and stuff like that. So there's a lot out there, which is a little terrifying sometimes.
Do you foresee a field trip to Mars or the moon maybe?
The question was, do I foresee a field trip to the moon or Mars? Not in the near future. I am one of those people that would go into space if I was presented with the opportunity, but I'm not sure how likely that is. This Mars might be as close as I get.
In terms of supporting living organisms, what's known about the subsurface of Mars, since the temperatures at the surface only warm up in the sun, and presumably that only penetrates so far?
Yeah, so the question was about microorganisms living within the subsurface and what the conditions are like to support them. So if there are these subsurface brines, those potentially, so a big thing for life is liquid water, as we know. So there could be microorganisms living in these subsurface brines where even though it's very cold, there could be high enough salt content that they're still liquid. I'm not a biologist or a geologist, so I always get nervous answering questions like this. But we see conditions similar to that on Earth, like very extreme conditions under the surface of the Earth. So actually, one of my colleagues who I went up to the Arctic with has done work, I believe, in like abandoned mines where the conditions are just like crazy high pressures and weird temperatures, and she was looking at the microorganisms that are somehow eking out an existence down there in the absence of anything that could normally support life. So we could be seeing something similar to that. Yeah. So the first question was, could those methane plumes be the result of meteorite strikes or volcanoes? There's currently, okay, I shouldn't say this. There are currently technically active volcanoes on Mars. The terminology for active volcanism is very confusing to me because they have not erupted in many, many millions of years, but they're still technically active, I believe. So it's not likely that it's that, because we would see other evidence of like active volcanism. In terms of meteorite strikes, again, we would probably be seeing other evidence of that to go along with the methane plumes. So obviously, we haven't directly observed any impacts near Curiosity or anything like that. I don't know, maybe there's a possibility, but I honestly, I'm not sure I can speak very intelligently to that. I do know that we have been able to detect meteorite strikes. One really cool one recently was when InSight, which was a mission that had a seismometer, actually saw the seismic signal of impact, and then one of the orbiters was able to image that exact same impact. So we are able to see these things, and it doesn't seem like they're connected to these methane plumes. And then the second, what was your second question? Yeah, so in this case, no, because none of those other rovers or landers had the same, they basically didn't have a version of SAM-TLS. They didn't have anything that could detect methane in the atmosphere. So unfortunately, we weren't able to see that. But we do love doing network meteorology in general, especially with Perseverance, because Perseverance is, just to go off on a tangent, Perseverance is about 10 degrees north of the equator, but it's in a similar area, like in terms of longitude. So we're actually able to observe clouds with Perseverance, and with Curiosity, we're able to observe like dust events with both of them. So that's really interesting, and we do like to do a lot of coordinated observations.
InSight was amazing. It shows us that Mars is still geologically active.
Yeah.
So there's a heat source there. So how strong is the heat source? I don't know. Geologists, whenever they want to find something out, they drill a hole. So that used to be the next mission to Mars: drill a big hole. But has anybody, like a geochemist that you collaborate with, has taken an analog for Mars soil, add some water, throw a little nickel in it as a catalyst, heat it up and see what happens?
I don't know. So the question was, has anyone taken a Martian soil analog and added water and a catalyst and seen what happens? Possibly. I don't know. I do I'm assuming someone has. Because I do know along those lines, there was a theory about how methane was being destroyed, that it was through like interaction of methane and like what's called triboelectric discharge, which is what you get when you eat leftovers and they spark. So the grains moving, can actually create small, electrical discharges between them. And potentially, so they simulated this in the lab. And they saw that it was able to destroy methane that way. Unfortunately, we haven't seen evidence of traveling electricity on Mars, and we actually did look for it with curiosity. So it seems like maybe that's not the destruction mechanism. But all that to say, there seems to be a lot of laboratory experiments going on, so I'm assuming someone has and is not aware of it.
Go ahead.
Are there other planets in our solar system or perhaps beyond where the search for methane might be fruitful?
So yes, Titan is full of methane. So Titan is one of Saturn's moons. It actually is the temperatures and the pressures are such that methane liquefies on its surface, so that there are these lakes of methane. So methane kind of, as someone who does not study Titan, methane acts kind of like water there, and there are methane cycles like this. So there's methane in a number of places in the solar system. Not, to my knowledge, necessarily indicative of life. So I think I know Titan has been like proposed as there could be some kind of life there. I think due to the presence of methane and due to the just the ways that it acts kind of like water there. Yeah, I don't know. I think potentially if we found methane behaving in an interesting way somewhere else, then that could definitely be interesting to study. But I'm not super aware of anything else, anywhere else that it's displaying the same characteristics as it is like on Mars. And honestly, that could just be due to how well we study Mars. Like we observe the heck out of Mars, so we know a lot more about it than we do about pretty much anywhere else in the solar system other than Earth, obviously.
I'll ask the last question.
Okay.
I can come to the mic. So it's a two-parter.
Mhm.
The first question is, and maybe we don't know this, but you know the lakes you went up to, the springs you went up to in northern Canada? How do we even know that? How was it even discovered? And you know, and I'm just, you know, there's so much out there. So how did we discover it? And the second one is when you see that methane plume, you said we catch it in the middle, but we also know these rovers travel very slowly. So how are we catching it in the middle?
Okay, so for your first question, I don't know exactly how they were discovered, but the first like papers that talk about them are from the 60s, when researchers from McGill and other institutions, I assume, like were first kind of founding the McGill Arctic Research Institute up there. So Axel-Heiberg Island has never actually been permanently inhabited, but it has had some indigenous presence as like more nomadic people passing through hunting or whatever. So I'm not sure if they were aware of it before, but the first characterizations of it come from the 60s from these geologists. In the literature. There are honestly probably a bunch of other sites like this that are in various places. I don't super understand all of it, but the way that permafrost and the way that the freeze-thaw cycles kind of work up in the Arctic is really interesting. So there are probably like a lot of, as you say, sites that we haven't looked at that could be very interesting. Okay, the plumes. I guess when I say we catch them in the middle, it's not entirely clear that it's the middle. It could be like a fall off on one edge or the other. And when I say the middle, I mean the middle in terms of time. So the plume could also be like the methane that we see could be traveling in from somewhere else, like blown by the wind or something. It becomes difficult to say because a thing about Mars is that it hates to have its wind studied. So when Curiosity got to Mars, when it lands, a bunch of small rocks and stuff get kicked up and the wind sensor broke. So we kind of fixed that a bit for Perseverance, we thought, and then Perseverance got to Mars and its wind sensor broke. So we don't know anything about wind on Mars, so it makes it slightly difficult to understand how wind might be bringing in methane from other places. But yeah, even if the rover is moving slowly, potentially, we don't have to be like right on top of a methane source because the methane could be coming in from somewhere else, potentially.
All right, that's Alex. Thank you so much.